network, that is backpropagation neural network. Okay, so this is one of the most important neural network, which is having wider range of applications in various engineering applications. So backpropagation neural network. Okay. So if you notice the mini ADA line, what was happening was, we have one hidden layer, and we have checked the error term at the output layer, and then we have adjusted the connection weights between input to the hidden neurons. Okay, and we have kept the connections between hidden to output. Those connections are not changed, so they remain unaltered during the learning process of mini ADA line. But backpropagation neural network is going to follow a different approach. So we are going to address the weight changes both at input to the hidden neurons as well as hidden to the output neurons. So essentially, when you look at the network, it is a multi-layer network. So it's a multi-layered network. Then it is feed-forward network. So the activation propagates in the forward direction. Okay, so it's a feed-forward neural network, and the training happens through backpropagation. Training happens through the backpropagation. When I say backpropagation, what is that you are propagating back? You are propagating the error is getting propagated. Okay, so if you see the network architecture, let me copy the network architecture. The book. So if you notice the network architecture here. So this is the network architecture. Are you able to see all of you?
Yes, sir.
These are all your input connections. These are all your formal inputs, and this is the bias. Okay. So this bias input is there for every node. Okay. So you can notice that bias input is going to the H1 as well as so on HJ and HP kind of a thing, right? And it is fully connected. In this case, X1 is connected to H1 and all the P number of nodes in the hidden layer. So there are about M neurons in the input layer, and there are P neurons in the hidden layer, and there are about N neurons in the output layer. Okay, and in this case, all are connected. Okay, and of course, in the diagram we have seen only one hidden layer. Depending on the problem, you may have one more hidden layer or two more hidden layers kind of a thing. So this is how the activation propagates in the forward direction from your input to the hidden units, and from subsequently from hidden units to the output units. And since your network is a supervised network, so I must say that this is a supervised environment. So every node in the output will have a target. So that means you will have T by 1, T by K, T by N. So every node in the network output layer will have the fixed target. So imagine you are giving some input like say 1, 1, so on, say 0, so on 1. So for that, target may be say 1, so on, say 1, say maybe 0, so something like that, depending upon the number of nodes in the input and output. So targets are all fixed. So then what happened, this network, once you propagate the activation from input to the hidden and similarly from hidden to the output, we calculate the error at output layer. Calculating the error at output layer is somewhat easy in the sense you have known target at the each node in the output layer. So what you typically you can do is like, I can say that my target minus actual output I can consider for calculating the error. Of course, it is not the only term that I'm going to consider. There is a different way of doing error calculation here, but I can say that t minus o I can do. So once you calculate the error, that error gets propagated to the hidden nodes. Remember, when it is getting propagated, that means you are going to multiply that particular error term with the corresponding connection weights. Okay, say take an example, del y1 is the error term at y1 node. When it is getting propagated back to h1, you are going to multiply the connection weight of w11. That means, the connection weight between the hidden node h1 and y1 would be multiplied with the del y1. Similarly, the error term from yk gets propagated to h1. So this error del yk gets multiplied over the corresponding connection weight. That is how the error gets propagated from output to the hidden. This is clear what I am talking?
Yes, sir. Sir,
All
can
of
you
you?
repeat once, sir, briefly?
Yeah, yes, yes. So let us take yn. We have, see, n number of nodes in the output layer. We said every node in the output layer has a target value that is fixed. T's are given. So what we do is we calculate the error for the output layer. Imagine that error is called del yn. For the case of neuron yn, it is called del yn. It is represented with del yn. This error will get propagated to the neurons in the previous layer. Say take an example, yn is propagating its error to the previous layer nodes. That means hidden layer nodes. When it is propagating, what it will do is that error value will get multiplied over that corresponding connection weight. So take an example, when del yn is getting propagated, it gets multiplied with the corresponding connection weight. So here the corresponding connection weight between HP and yn is this particular weight value. Similarly, when it is getting propagated to this particular Hj, corresponding connection weight, it gets multiplied. Similarly, the del yn and H1. So corresponding connection weight and this del term will get multiplied. That's how error value from one node gets propagated back. So when it is going like that, look at H1, okay, the hidden node H1. So for hidden node H1, error is coming from Y1, Y2, and so on Yn. Is it not? So error come from del Y1 comes, error from del Y2 comes, error from del Yn also comes. And when it comes, these values gets multiplied and come. So del Y2 multiply with corresponding connection weight and comes. Del Yn multiply with corresponding connection weight and comes to hidden node H1. That is what we are discussing. Is that clear? Hello? Are you able to follow?
Yes, sir. Clear.
Anyway, we will be taking one problem and then we will try to solve that. Now, we calculated the error. We are saying we have done error at output layer. Now, is it the connection weights only these connection weights? No, we have connection weights here also between hidden to input to hidden. So obviously we have to calculate an error for hidden as well. But calculating error for hidden is somewhat tricky in the sense, since you know the target values. Remember, target values are given for output nodes or even hidden nodes. Generally, target values are given at where? Output or hidden?
Sir, output.
So when you have target values given for only output nodes, you don't have target values for the hidden nodes. But when you are calculating the error, what generally so far when you take any of the previous learning approaches, whenever you have a target, obviously what we did was we just made it as like a target minus actual. We have that term actually. But when it is coming to the hidden nodes, certainly you will have no targets. So how to calculate the error? Okay. So these are the interesting things that we need to remember and do it. Okay. So the aim of the network in the backpropagation model is, so the aim of the network, the aim of the backpropagation network is to achieve balance between two things. Number one, memorization. Number two, generalization. This is the important aim of the new backpropagation network. Okay. When we say memorization, have we discussed these two things, memorization and generalization, earlier?
No, sir.
Okay.
No, sir.
So, okay, I thought we discussed. So the memorization means the ability. See, what is meant by a memory? You know, you learned about about something, and when it is presented back to you again, you will recall it. So that means ability to respond correctly to the input patterns that are used for training. Okay, that is what is memorization. That means, imagine if I am saying that, look, when I give the input pattern of say 1 1 0, you are supposed to produce or recall or submit the output as 1. So 1 1 0, my output, target output is 0. If I say that, and if I produce the input 1 1 0, the network should give me back 0 upon the training. Okay, once you train the network, training is complete. When you present the pattern, and the network is supposed to provide the answer for which it was trained. So ability to respond correctly to the input pattern that are used for training. What is generalization? Now, is it that always do you provide the inputs that are already trained? Certainly not. So the ability of the network to give reasonable response, to the inputs, that is in similar to the trained patterns but not identical, right? So means what actually, in the class we are solving some problem. In the examination, if I give you the same problem and if you are answering that in the examination, that means you are memorizing it. In the class we are solving some problems, and in the examination I am giving you a different question. When I say different question, of course on the same topic, say on the perceptron learning or on the Hebbian learning, or say take an example on the backpropagation. I am giving you a different network with the different input values and target values. The problem is different, but of course on the backpropagation. Will you solve it or not in the exam?
Yes, sir.
That's what is generalization. So we humans are having the ability to memorize, number one, and also have the ability to generalize based upon what we have learned. So the backpropagation neural network is aimed at achieving these both abilities, memorization and as well as generalization. Okay, so that is the reason why this particular network is able to solve various interesting problems in several engineering applications. The reason is simple, as I said, it is able to memorize, means when you train the network is able to remember the things. You see here, another thing you need to follow. See, I hope you have closely observed the problems so far we have discussed. Say take an example, AND gate, and you take any learning algorithm. Okay, say take an example, perceptron learning algorithm, AND gate. So you give first input, say 1 1, you get an output 1, and the second input pattern, third input pattern, fourth input pattern. Remember, step 1 you present one input pattern, you modify the weights. With the modified weights you are presenting the second input pattern and you are modifying the weights. Then presenting the third input pattern, modifying the weights. Will the network say that, look, after completing your third step, will the network say that, look, you have given the input of third input pattern, now my weights are changed, I will not work for the first input pattern? Is the network is telling like that? Our network is behaving like that?
No, sir.
So that is what is that ability to memorize. So though weight values are existing, the values are adjusting in such a manner that whatever that network has learned with regard to the weights, the adjustments that are made, that are not lost. So slowly when you say that the network training is complete, you have found out the weights. Those weights are working for all four input patterns. Okay, whether you say 1 1, 1 minus 1, minus 1 1, minus 1 minus 1, all for four input patterns the network is working. It is not saying that no, I forgot for the first input pattern, now I have learned the fourth input pattern, so I forgot the first input pattern. No. So in the similar context, the memorization here with regard to the backpropagation learning algorithm is that you, of course, what we discussed is the simple problems like AND gate, OR gate. These are all very, very simple problems. If you see the practical application, you will be having the number of feature vector would be quite large. Okay, so and number of such samples would be also large, right? So the network is able to memorize, number one. Number two, when the network has presented with a pattern on which it was not trained, still the network is able to classify the given input pattern. It is not saying that no, I was not trained on this particular pattern. So that's what is generalization ability. Okay, these are all both important aspects, and the backpropagation is able to achieve the right balance between both of them. So when you see the training in the backpropagation, happens in 3 stages. Okay. Number 1, you provide feed forward input training pattern. Okay. So first you provide the input, then calculation of error and backpropagation. Then updation of weights. So these are the 3 stages that are there in the backpropagation. So you present the input from input layer to the hidden layer, then hidden layer to the output layer, then calculate the actual outputs. So this is how the feed forward activation propagates in the forward direction. Once that is done, start calculating the error. And once the error is calculated, propagate it backwards. Okay. So let us see with the algorithm of the backpropagation. Then before algorithm, what I will do is I will keep the flow chart for better understanding purpose. A simple flow chart of the backpropagation. So this is the flowchart of the backpropagation algorithm. See, there are so many heuristics again in this. We will discuss about those heuristics in a different class. So you begin the learning process. Take some small random weights across the connections. Then what you do is you take the first input, apply the activation and submit the input to the network and propagate the signals. When I say signals, you are submitting the input. So propagate the net input pattern from the input layer to the hidden layer and find the activations at the hidden layer. So that means you calculate the net inputs to every node in the hidden layer, as well as you calculate the output from the hidden layer. That means you are once you calculate the output from the hidden layer, you are calculating the input to the output layer. Then you calculate the output from the output layer. So let us take one simple network. So imagine that x1, x2, and z1 and z2, and this is y. This is bias, and this is bias. This is bias. Okay. So what actually we are doing is first what we do, we calculate net z1, then we calculate net z2. Then after that, what we do? Can somebody tell me what we will do?
So we find out the inputs for the Y.
Yeah, f net z1, that means output from z1, right?
Yes, sir.
So Next we calculate f of net z2. Then we calculate net y. Then finally we calculate f net y. These are the propagation of the signals. That means this is what actually we have done. Then what we do is, okay, typically this f, whatever we said, the activation function, you can take f is equal to 1 by 1 plus e power minus lambda net, okay, which is the unipolar sigmoidal activation function, or else you can take a bipolar sigmoidal activation function, which is 1 minus e power minus lambda net by 1 plus e power minus lambda net. And remember, this take lambda is equal to 1. So this f becomes f is equal to 1 by 1 plus e power minus net. That's how you are going to calculate the f. Okay. So your activation function f of net z1, f of net z2, then you are going to apply the activation function f of net y. Now the point is, depending on the problem, if you want to change the activation function, you can apply one activation function at one hidden layer. So that means all the neurons in that particular hidden layer follows that particular activation function, and a different activation function at the output layer. It's also possible. But generally, while solving our book exercises and exam related questions and all that, we don't take two activation functions, one at hidden layer and one at output layer, and like that we don't do. We follow only one activation function. Okay. So once that is done, we have actually ty, right, which is target y. Is it not? Then what we do is we calculate del y, which is error at the output layer. So error at the output layer is calculated based on, there is a formula for that. Okay, we will discuss those formulas little later. So the del y I will be calculating it. Once I calculate del y, I need to send this back to the Z1 and Z2. So I need to calculate del Z1. I need to calculate del Z2. Once I have these terms, then weights gets updated. So I need to modify these connection weights. When I am modifying these connection weights, I will be considering del y. When I am modifying this connection weights between hidden to between input and hidden, I am going to consider del z1 and del z2. Is that clear?
Yes, sir.
Anyone else here? Any doubts? Of course, I have not said how these calculations are weight formulas and all that, but the
Sir, can you
process.
explain the last point once more?
Yeah. So what we said was, for every node at output layer, first we calculate the error term. Of course, when I say every node in the output layer, in this particular problem, what I have, or the diagram I have given, you have only one node in the output layer. So I'm going to calculate the error term called del y for the output node. Now remember that del y gets propagated. What is meant by backpropagation? The error gets propagated. The error is propagating back to the hidden nodes. I said few minutes back, when it is getting propagated, we are going to multiply the error term with the corresponding connection weight. So that's how it gets propagated. So you propagate it back, and then calculate error at hidden nodes. So this is error at output. This is error at hidden. So these two are error at hidden. This is error at output. Now you calculate del z1 and del z2, that means error at the hidden. Now once you have these error terms ready, your weights have to be modified. When I say the weights between hidden to output, these are the hidden to output, right? Weights between input to hidden, these are input to hidden. These weights have to be modified. When I am modifying the weights between hidden and output, I am going to consider the error term that is there at the output layer, that is del y. When I am modifying the connection weights between input to hidden, I am going to consider the error at the hidden nodes, that is del z1 and del z2. When I am modifying the connection weights, okay, is that clear?
Yes.
So you have seen the process. Now let us see how these errors are getting calculated. And remember, we are going to fix the activation function, unipolar activation function, 1 by 1 plus e power minus lambda net with lambda is equal to 1. For our convenience sake, of course, you can even have the, you can have the bipolar activation. That's also possible. So each unit, okay, let me draw once again the network what we have taken: x1, x2, z1, and z2, z1. Of course, this is a very simple network. In a practical, you may be having larger networks. So we have already done this. The net inputs, net z1, net z2, then fnet z1, fnet z2, then net y, fnet y. All this is done. So now we are focusing on the error term calculation. So each output unit has target, right? So what we are going to do is we are going to compute the error as del k, or it's del y, whatever you call it as, del y, del k, whatever it is. So corresponding target at that particular node by k, that means the actual output, and the f dash of net yk. Okay, so this is how we are going to calculate the del k. So that means imagine if your output node is k, del k is equal to target minus actual f dash of net k. What is this f dash is? Net k is your first derivative of the activation function. Now imagine your activation function, we said, is 1 by 1 plus e power minus lambda net. Okay, that's what we said. So in such case, what happens? This f dash net is f dash net y is equal to your lambda into, of course, lambda we are going to make it as 1. So lambda into f of net y into 1 minus f of net y. And remember, this holds only for this activation function. Imagine if your activation function is different. Imagine if your activation function is different, your derivative of that active, based on the derivative of the activation function, your f dash net varies. Okay, so how we are going to write this del k? So del k is equal to target actual into the lambda into your f net yk to 1 minus f of net. This is how I am going to calculate error for the node y. Okay, is that clear? Is that clear?
Yes.
Imagine if it is activation function is bipolar sigmoidal, then del k is equal to tk minus yk into lambda into half 1 plus f net yk into 1 minus f net yk. Okay, if it is activation, if your activation function is a bipolar activation function, then your del k calculation is like this, because it depends upon your first derivative of the activation function. Okay. So then what happens? This is wz1y. This is wz2y. Okay. So we calculated error term, that is delta for the output unit. Okay. So the error gets propagated, and now we are going to calculate del z1 and del z2. We need to calculate. So how we are going to calculate the del z1? When I am going to calculate the error term for z1, since you have only one node in the output layer, so the output layer node y is propagating its error to z1. What is output error term at the y? That is your del y or del k, whatever it is, del k into w z1y. Okay, are you able to follow? Hello.
Yes, sir.
So similarly, this is del k into wz2y. The error git is getting propagated, and f dash of your net z1, that means output from z1. Here also you have to apply the function, your first derivative of the output from z1. So activation function at the z1. Okay. So this is the error coming from the output node. Similarly, this is the error coming from the output, and this is the derivative of the activation function at the hidden node. And similarly, this is the derivative. So this is error at hidden node 1, error at hidden node 2. So this is error back propagated from where? From the output node. Okay, is that clear?
Yes, sir.
Now your f dash net z1, again you have to calculate. You have to calculate how you have to calculate, like how we have calculated here. So f dash net z1 we are going to calculate as, since it is a unipolar activation function, what happens, your del into f net z1 into 1 minus f net z2. So you have to expand this as del into f net z1 into 1 minus f net z1. And similarly, this also you have to expand lambda f net z2 into 1 minus f net z2. Okay.
So this is for unipolar, right?
Yes, yes.
Okay.
This is for unipolar. Yeah, unipolar. What I have written is for unipolar. And of course, I have already given for bipolar for the output. The same logic holds for the bipolar at the same logic holds for the bipolar at the hidden. Okay. Is that clear?
Yes, sir.
So what we have done was we calculated del y. Don't get confused. I written here as k under the notion that is the this one, but either it is del k or del y, both are same. So the del y, and we calculated del z1 and we calculated del z2. Okay. Now the point is the errors are calculated, and if you closely observe, when you are calculating the error at the output layer, you have the parameter called t. Now when you are calculating the error at the hidden layer, you don't have t, okay, because you don't know the t, and certainly t cannot be given for the hidden layer nodes. Okay, so that's the reason why you are going to have this. So is that clear?
Yes, sir.
Yeah. Now the point is how you are going to adjust the weights. So again, you have two layers. So weight modification at output layer is the new weight is equal to the old weight plus your learning constant alpha into your del k or del y, whatever it is, and your uh, what we have written here is the output. So imagine this is output at node y. Imagine that is generally we write that output as f of net y. Okay. Okay. So the old weights, learning constant, error term, actual output at the node. This is how I'm going to modify the connection weights at the output layer. So at hidden layer, the new weights are equal to the old weight plus the learning constant, and the error term for the jets, okay, either jet 1, jet 2, whatever it is, and the corresponding input at the node. Okay, this is the weight modification formula for the hidden layer nodes. Okay, so weight modification at output layer, weight modification at the hidden layer. So if you notice, okay, this is learning constant. These are the error terms at hidden units. Right? We have actually in the previous we have seen diagram. Here we have two hidden units, so del Z1 and del Z2. So when we are modifying these connection weights, the connection weights to Z2, then obviously we are going to consider del Z2. When we are modifying the connection weights to Z1, we are going to modify the del Z1. Okay. So this is the weight modification formula. I think today we discussed the process. Then we will take one particular problem and then solve it in the next class. And similarly, those who are really interested and those who have actually followed what we discussed, probably you guys can take one sample problem at the book back exercises and then try to solve it. Are there any doubts in the total overall process what we discussed?
Sir, here the weights at the hidden layer are the weights from the input layer to the hidden layer, right? Sir, the weights that we need to
Yeah,
modify.
this, yeah, here, right? Here.
Yes, yes.
So this is input to
Hidden.
input to hidden layer connections.
Okay, sir.
And this is hidden to output layer connections.
Sir, can we leave?
So the point is, remember, just for the case of our understanding purpose, we have taken only one hidden layer. Now the problem complexity increases with more hidden layers. In the sense, then what will happen is, imagine you have one more hidden layer. You are going to propagate the error from hidden output layer to the hidden layer that is next to it, calculate the error terms, and propagate those error terms to the another previous hidden layer. I hope you are able to follow what I am talking. So imagine you have two hidden layers. So this
Sir,
is one.
can we leave?
Yeah. If you have a class, you can proceed. No issue. If you want to leave, you can leave. No issue. So I'm going to stop in next 5 minutes. So this is hidden layer 1. Imagine this is hidden layer 2. Okay. And this is your output layer. Actually, so far we were discussing with only one hidden layer. If you have two hidden layers, the error term propagates from output to hidden 2. Error term propagates from, so this del y, and you are going to calculate del terms here, and those del terms gets propagated back to the hidden 1. Okay. With the same logic. So this is how the process works, and the important thing is calculation of the del terms. Okay, and remember, with your activation function, the again del terms calculation varies.